Hello and welcome back to this course on advanced plasticity of solid continua. In this lecture we will be discussing the physics of yielding and the classical yield criteria, only the basics under small deformation, right. So, let us start. Now, so it is understood, of course, that you are more or less familiar with the elasticity theory. Now, so I can assume therefore that you know, let us say under small strain, linear elastic response would be typically given by this kind of an equation, right. So, it is basically the stress given by the elasticity tensor, which is a fourth order tensor, times the small strain, right. Now, whenever we are talking of small strain, please recall that we are talking only of one configuration. We are not discussing about both referential and spatial configuration, because small strain corresponds to a definition which uses displacement, which is basically a function of only the referential coordinates, a function that lives in the referential body, right. We have discussed this once. So, and we know that elastic responses are reversible, right. So, and sigma, which is the stress, we do not have to bother where the stress lives, it is always in the referential body as functions, okay. So, stress is basically some elasticity tensor times, by times I mean an inner product with epsilon, right, small strain. Plastic response on the other hand has a major irreversible component, right, because the defect microstructure moves, evolves. And so, macroscopically what we see as plastic deformation is possibly something like a strain like quantity, we can call it plastic strain. For example, you remove all the forces and then you will see some permanent deformation of the solid, right. So, that is what we roughly call as the plastic strain, or that is the result of some plastic straining, right. So, because plastic strain really does not have a very clear transparent geometric structure, so therefore, we typically call plastic strain as an internal variable. It is not a geometrically meaningful variable, right, like deformation gradient is a geometrically meaningful variable, plastic strain is not. Now, yielding, which is the plastic yielding, it basically marks a departure from a purely elastic behavior in the form of dissipation setting in, right. So, before we discuss this, there is one small aspect that I need to bring to your notice, that is, we will be discussing small strain elasticity, which will transit to plasticity. So, small strain elasticity, so we will be basically, when the small strain elastic solid is being considered by us, we will be only restricting ourselves for the time being to an isotropic elastic solid under small strains, right. So, in this context we need to understand a little bit what basically is the isotropic elastic solid. You may already know what isotropy is, but probably not exactly in this language. I will just try to quickly refresh your memory if you already know, or let you know about the mathematical basis for the isotropic elastic solid, because it is also an important aspect of small strain plasticity, because elastic response is part of the overall response of the solid. So, it is here that we need the notion of what is called material frame invariance. So, we already have understood the concept of objectivity, where we do a change, a rigid body modification, through rotation and translation of the coordinates frame of the deformed body, of the spatial configuration. But we have left the material frames unchanged there, but now we do just the opposite, okay. For small strains anyway there is no spatial body, so we have only the material body or the referential body, right. So we have the referential coordinates, and we actually are talking about the rigid body rotation of these frames, these coordinate frames. Okay. So these rotations, as you know, are typically captured by the special orthogonal group, you know that. So Q is a proper, orthogonal tensor, which means that Q transpose Q is identity and determinant of Q is 1 plus 1. So we say that Q belongs to SO3, that is the special orthogonal group. Why is it called a group? Please recall, I have already told you that any composition of two rotations, if Q1 is one rotation and Q2 is another rotation, then Q1 Q2 or Q2 Q1 for that matter will also be a rotation which will belong to SO3, special orthogonal group. Identity rotation, which is no rotation at all, leave the body as it is, okay, that also belongs to this SO3. And moreover, the inverse of the rotation, which is basically Q transposed, if Q is the rotation, also belongs to SO3. These are the three requirements of forming a group. Now let us consider phi as a scalar valued function of some matrix A, 3 by 3 matrix field, right, 3 by 3 tensor A. Now let us also assume that this A belongs to either lin plus or sim or p sim. I will explain what these are. So A is, if A belongs to lin plus here, then A is basically a positive definite tensor, strictly positive definite. If it is sim, it is a symmetric tensor. If it is p sim, it is symmetric and positive definite, right. The important thing is that this definition is the important thing here. So if I do now a frame change, a change in the coordinates of the referential body by a rigid body rotation Q, then we say that this phi of A is invariant under this rotation or under all rotations, invariant under SO3 itself, if for any such rotation Q belong to SO3, phi of Q transpose QA Q transposed is equal to phi of A. That means the field phi A is not affected by such rotations of the material frame. In case there is, instead of a scalar valued function, we have a tensor valued function T of A, where the result of applying T to A is itself is a 3 by 3 tensor, right. Then it is called invariant under SO3 if T applied to Q A Q transpose, that is under a change of frame with rotation Q, will be equal to Q T of A Q transpose. Okay. So this notion of material frame invariance is very important in defining the various material classes. I will now explain that through a quick discussion on what are called material symmetry groups. Okay. So a material symmetry group, so you think of some material like wood. You know that wood has different strengths in different directions. It has some kind of striations, right. So if you pull wood in a certain direction, it will not stretch that much as it would if you were to pull in another direction, right. So the question of material symmetry group is related to the issue of if you rotate the coordinates in the material body in the undeformed configuration or the referential body, then would the response, would the way that the material orientations are, would that affect the response? That means would you get a different response or would you get the same response? That is the question, right. So basically you see that unlike the whole of SO3, any rotation, under any rotation it cannot need not be the same response, right. So because the solid that you are considering may be hard in certain directions, may be softer in some other directions, right. So you will have to understand the material symmetry group as that subset of rotations under which the material response will remain exactly the same. Okay. like bimaterial response, for example, the strain energy remains exactly the same, right, or even the stress. The thing is, or the stress will change according to this relationship as shown here. Okay. If it is a stress, if it is a strain energy like thing, then it is a scalar field, then it will remain the same. Okay. So you see, so therefore this subset of Q's rotations, which basically is a subset of SO3 itself, call this subset as M, under which the material response remains the same, okay, irrespective of whether you change the coordinate or not. That is called the material symmetry group. All right. So let us consider a specific example. Okay. Let us say that a deformation gradient, I am creating a new deformation gradient F tilde first by applying a rotation Q, okay, and then applying the actual deformation F. Q is also a deformation. So then the C tilde corresponding to this composite deformation gradient F tilde will be QC Q transpose, where C is the Cauchy-Green strain corresponding to F. Okay. Then if I write the strain energy as a function of this Cauchy-Green strain C, then the material symmetry, if Q is in the material symmetry group here, then the material symmetry implies that the strain energy computed via C corresponding to the deformation gradient F would be the same as the strain energy computed with the frame, the material frame rotated by Q. So that is psi of Q C Q transposed. Okay. So therefore Q is basically a material symmetry, one of these elements of the material symmetry group. Okay. So with this basic introduction to what is happening to the material symmetry, we say that an elastic material is isotropic, right, if this material symmetry group is the entirety of the SO3. That means any rotation leaves the response, such as the strain energy, unchanged. You get the point. So this is the correct definition of isotropy. Now under small strain, as you may be knowing, the elasticity tensor for an isotropic solid has just two unknowns in general. For the most anisotropic solid, elastic solid, you have this elasticity tensor consisting of 21 unknowns, right. But for an elastic isotropic small strain case, you have just two unknowns. In this particular case, you can write psi. Now we should not bother about the strains like C, the Cauchy-Green, because it is for large deformation. Let us consider a small deformation case. So psi will be a function, strain energy will be a function of small strain epsilon. It will be written as half of epsilon inner product with C inner product with epsilon. You understand that C epsilon, this part, so the C epsilon, this part is essentially the stress, correct? This is the stress sigma. You understand? So basically, therefore we are saying that if we define stress this way, therefore it is half of sigma inner product with epsilon. That is the density of free energy or strain energy, whatever. Now the thing is that in this particular case, this sigma, the stress, can be written in terms of two unknowns. We already said these two unknowns are this mu and lambda. These are called the Lamé constants. Okay. So mu is correspondent to, as you know, to the shearing effects, and lambda corresponding to volume change effects, right. So you see that sigma is a linear function of the strain epsilon, right. So because stress is a linear operation on epsilon, okay. So it is a linear function. Now you can actually write this sigma also alternatively, not necessarily in terms of Lamé constants. You can write it also in terms of elasticity constants like there's Young's modulus and the mu, that is the Poisson's ratio, okay. So but you will always need two constants, not more than that. Now, having talked about these isotropic elastic solids, let us see what the origins of plastic flow could be. So, let us talk of metals first, which have a crystalline structure, right. So, these crystalline solids you already know because of the first lecture, they plastically deform by typically dislocation motion, right, and there are other effects also. So, dislocations, as you know, are basically line defects in lattices in the crystalline structure, because some atoms are missing in their positions, right. So, the slip, the plastic slip basically occurs if you look at a microscopic perspective, then they occur on crystallographic slip planes because of shearing. The shearing occurs because of the external loading, all right. So, other defects, so dislocation is basically a defect that destroys the translational symmetry of the crystallographic structure. That is the language of the material scientists. So, other defects like disclinations that destroy the lattice's rotational symmetry, they may also actually contribute to the plastic flow, but it is known that for metals under normal temperature ranges, disclinations do not produce that much of, they do not have that such a profound effect on plasticity. It may have, but not a great deal of effect like dislocations. There could be other effects also, like grain boundaries, inclusions, interfaces, even cracks. If there are some microscopic cracks in the solid, they are also interfaces, right, and voids. They can also affect plasticity. Now, from a purely crystallographic point of view, if you look, then we can actually have a crystallographic slip planes. These slip planes will be denoted by a collection of such planes represented by some vectors m and n. So, so m tensor product n will define such a crystallographic slip plane, all right. So, if you resolve your stress, that means take a projection of your stress sigma on this slip plane, then you get what is called tau here, okay. All right. So, this tau is called the resolved shear stress on that slip plane, okay, along a specific plane given by m tensor product n. So, yielding begins according to Schmidt's hypothesis or law, that it says that yielding begins when this resolved shear stress reaches a critical value tau c, right. This is the crystal plasticity point of view, which we are not doing, but this may help in developing our models. But what we will be doing, we will not even recognize that there is a crystallographic structure, because at the macroscopic level there is no such thing. You do not see by looking at a metal that there is a crystal structure there, no, with your naked eyes. So, therefore, it is not a good idea for continuum plasticity. But on the other hand, let us also look at the possible resistance to plastic deformation, which can lead to hardening. We will not be initially discussing about hardening, we will be interested in mostly the perfect plasticity where there is no hardening. But it is important to understand the physical basis for why hardening may happen. That I have already discussed once, that basically if dislocations multiply and become a forest, then the dislocation motion itself may get impeded because of that. So, the question that arises is that how can dislocations multiply? So, one of these mechanisms is called the Frank-Reed mechanism, Frank-Reed source mechanism, right. So, this is actually written here. So, under shear, a pinned dislocation segment starts behaving like a bow, it bows, okay, becomes more and more bowed, till it joins in a circular form, okay, the two ends of that bow joins. So, it becomes a loop. So, there is a self intersection and a new dislocation loop is released, and the old pinned dislocation segment is reproduced. So, like that, new dislocation loops can go on getting released by a Frank-Reed source. So, this is basically the reason that why dislocations can multiply under external loading, right. This bowing takes place because there is an external load, right. So, this is the microscopic basis for hardening. If there are too many dislocations, there will be an impedance which will impede the motion of there will be the dislocations will find it difficult to move, right. Okay. So, the macroscopic observations here is that, I mean, we are not now looking at dislocations, we are looking at the continuum level description. In metals, typically it has been seen from experiments that plastic flow is more or less volume preserving. That means it is more or less incompressible. So, this means that the component of stress which basically drives the plastic flow must be purely deviatoric. Okay? If to jog your memory, I will come to the issue of deviatoric stress once more. That means the trace of the stress tensor, the pressure part of it may not really affect plasticity much. Okay? So, the pressure means the hydrostatic stress. This can at best weakly influence the yielding in such metals. So, in such cases, we must think of the driving force as the deviatoric part of the stress. Okay? Now, you can actually think of the decomposition of stress accordingly. So, you can decompose a stress tensor. Again, recall that we are not talking of Cauchy stress or this stress or that stress here, because of the simple reason that there is only one body for us under small deformation. Okay? I am repeating this because this has to be understood thoroughly, that there are no multiple bodies now under small strain. Okay? It is only the referential body. All the variables like displacement, stress, strain are looked upon as scalar valued or vector valued or tensor valued functions on this only unique body. Okay? So, the stress, which is a tensor valued functions on the body, will be basically written in terms of the deviatoric part, and this is called 1/3 trace of sigma times I is the identity matrix in 3D, that is 3 by 3 identity matrix. This part is basically called the pressure part or the non-deviatoric part, the volumetric part of the decomposition. This is the deviatoric part. Okay. So, sigma 0 is the deviatoric stress, this is the hydrostatic component. Now, this is an orthogonal decomposition in the sense of Frobenius, orthogonality. That is, what we mean is that if you take this Frobenius inner product of sigma 0 and 1/3 of trace of sigma times I, you can quickly check, you can actually calculate it, it will be a scalar valued quantity. No, you can calculate it especially based on the easiest way of calculating it is based on indicial notation using a coordinate. Okay. So, this will be turning out to be 0. So, like vector dot product, we also say that the matrices like this and this are orthogonal if this is true. Okay. Now, we come to the most important yield function concept. Okay. This will be a very important thing. So, the internal variables could be the plastic strain and hardening, okay, hardening variables, but initially we won't be considering hardening. Perfect plasticity means that the stress strain curve, if you look in 1D, this is stress, this is my strain, right, then it goes up and then it becomes a straight line like that. Okay. So, this is something like this. So, this is the perfect plasticity, no hardening. Now, the internal variable are still present in the form of something which is called the plastic strain. We will come to that, but then we need to define, to indicate the precise separation of the reversible and irreversible regimes of the response, we need to define a surface. Think about it, a surface basically in 3D, for example. a surface will completely separate two regions, right. So, similarly here there is a very sharp separation between reversible and irreversible regimes through a surface which is defined, this surface is defined by this function f equals 0, okay, that is a surface. F less than equal to 0 defines a closed region which is called the elastic region, alright. So, as I have noted here, f of sigma comma alpha, typically you look at f, this yield function, as a function of sigma. You assume that alpha is fixed for the time being, okay. So, you know, this defines the yield surface, right. So, now we have two cases. One is f can be less than 0, in which it is a perfectly elastic reversible response. So, anything that we have studied on elasticity theory is applicable. There is no plastic flow, and f equal to 0 corresponds to the possible plastic response. There is no guarantee that plasticity has occurred there, because it may so happen that it is on the surface, but at this point, but as soon as you increase the load further, it leaves that surface. In that case, starting from that point on the yield surface, the flow has not moved, right. So, just because f equal to 0 at the current time does not mean that in the immediate neighborhood of time, however infinitesimally small it is, it will remain on that surface, right. But this is a necessary condition for the plastic flow to occur. At least if a plastic flow is occurring, then f has to be equal to 0, okay. You cannot say therefore that plastic flow is occurring, that is why f equal to 0. So, that is why f equal to 0, so, but f equal to 0 does not necessarily mean that there is a plastic flow. So, you understand in this scenario, because there is a very strict separation of the reversible irreversible regimes, f greater than 0 is not admissible, right. So, any stress which produces f greater than 0 or any alpha that produces f greater than 0, that is not admissible, okay. So, typically let us talk about stresses here. So, the stresses for which f sigma is greater than 0 are inadmissible. F less than 0 is the elastic region. So, therefore, let us define the admissible set, call it C. It turns out that it is a closed set. It is given by all this sigma for which f is less than 0. As I told you, think of f right now as a function of sigma only. It also turns out that the way that we define plasticity, the models, C is a convex set. That is a very important point, and we will discuss about convex sets soon. But for the time being, let us understand this notion of an yield surface is a pure idealization. In practice, typically you do not have a very strict reversible irreversible separation. It may happen that even during the time when the gross experiments at the macroscopic levels are showing that it is an elastic response, very small plastic deformations would be occurring there, okay. Typically that is what is seen. That is why fatigue occurs. If you do the cycling for a very large number of cycles, very large number of times, then you get some failure, which should never happen if it is a perfectly elastic response. So, typically therefore materials, the real materials exhibit stress relaxation and creep. So, stress relaxation means that a strict separation is never possible. So, typical forms of these yield surfaces in classical plasticity is not consistent with that, and this class of models in plasticity, right, which creates this strict separation, they also have an additional feature often, which is the notion of rate independence. I will describe rate independence mathematically later on. For the time being, let us understand that rate independence is that property of plasticity wherein irrespective of the rate of the loading, provided the initial value and the final value of the load remains the same, that is the load difference remains the same, irrespective of how fast you are going from the initial to the final loading, final stress for that matter, the plasticity, the constitutive relation relating the stress to the strain rate remains independent of that. Okay? That is roughly the, so it is independent of the stress rates that way, okay, or the loading rate. Okay, so we will be discussing this notion far more appropriately, and it turns out that basically when the stress relaxation occurs, if that relaxation time approaches infinity, then you get this strict separation between the reversible and irreversible responses. So with this, we will just take a small breather and come back with the rest of this lecture. So till then, goodbye.